Okay, so we want to continue with section 2.1 on congruence and congruence classes. All we've done so far is define the definition of what it means for two integers to be congruent one another. And we did a theorem on the congruence on these integers are reflexive, symmetric, and transitive. So we want to continue now with theorem 2.2 that says if A is congruent to B mod n and C is congruent to D mod n, then A plus C is B plus D mod n, and AC is congruent to BD mod n. So if you think, suppose we removed mod n from all these and we just said they were real numbers, or integers if you want. So if we ignore the mod n, if A is equal to B and C is equal to D, you know if two things are equal and you add it to both sides of an equation, again without the three bars, A plus C is B plus D. We know this. We do this all the time when we solve equations. You add the same thing to both sides of the equation. You still have a valid equation. Likewise, if A is equal to B and C is equal to D, AC would be BD. We do that all the time. You multiply this both sides of an equation by the same thing and you have a valid equation. But we can't just say, oh, it's true for equalities, so it must be true for congruences, right? Congruence is not the same as equality, so that's why we have to prove this theorem. Okay, so the hypotheses are the same for parts 1 and 2, so let's just start with the hypotheses. So assume A is congruent to B mod n, and C is congruent to D mod n. If you look back, the assumptions have the same flavor as transitivity property on the last theorem, but we had A to B and B to C, so we have an extra variable. But if you look at what we're about to do, it's exactly what we did in the last theorem. Let's use the definition. Then, what does it mean for A to be congruent to B mod n? N divides A minus B, and for C to be congruent to D mod n, that means N divides C minus D. Now, what's the definition of divisibility? So hence, since n divides a minus b is n times some integer, I'll just say k1, and n divides c minus d means c minus d is n times some integer k2. Now I've introduced two variables, so you should say what they are for some k1, k2 in the integers. Okay? So remember we mentioned last time, and you did this in discrete math, when you have congruences, what do? Congruences to divisibilities to equations. We do stuff with equations. We'll go back to divisibility, and then we'll go back to congruences, because the conclusion has congruences. So congruences to divisibility to equations, back to divisibility, back to congruences. Okay, now let's think about part 1 here. A plus B is B plus D. Let's work backwards for a second, because again, I call this the no thinking part. I just went with my gut, right, using definitions. So let me write over here where we're trying to get to A plus B is congruent to A plus C. A plus C is congruent to B plus D mod n. Well, what would that mean? That means n divides the difference, A plus C minus B plus D. So we need A plus C minus B plus D to be n times some integer. That's what we need. Okay? So we need A plus C minus B plus D is n times something. Well, from these equations, how can we get this equation? So I need an A plus C minus a B plus D, and eventually that has to turn to n times something. Well, notice I have an A minus B here. Now that's not A plus C, but I have an A minus B and a C minus D. If I add those two together, you get A minus B plus C minus D, but that is this, right? It's A minus B plus C minus D. It's the same thing. So if I start with this and rearrange, I can get A minus B and C minus D and then replace them with the NKs. So that's what I'm going to do. Okay, so I'm going to continue here. Therefore, okay, now again, I'm writing this because that's what I want my final equation to look like. Therefore, A plus C minus B plus D. Now it depends on how much work you think the reader needs to see. I'm just going to do the rearranging, and hopefully a reader would see this. This is the same as A minus B plus C minus D, right? A minus B, C minus D. When you distribute the minus sign, and then equals. Now A minus B we just said was NK1. C minus D we said was NK2. So again, trying to work backwards. This is what I need to be N times something. I started with that, I rewrote it, so then the reader would see that I'm using these over here. If I just jump to here, the reader may not understand. Remember, when you're writing a proof, you've got to think about your reader. Don't make the reader do the work. You're doing the work so the reader can follow your proof. But I need this to be N times something, so I can factor the N out. So I have A plus C minus B minus D is N times an integer. I said K1 and K2 are integers, so the sum is an integer. And now we just have to go backwards from what I just erased. We conclude that since A plus C minus B plus D is N times something, N divides A plus C minus B plus D. And right, that's the definition of congruence. That means A plus C is congruent to B plus D mod N. Okay, so here. I should really tell the reader, since there are two parts, how about result one? Result one now follows. That tells the reader I'm done with this proof. I might have considered, I kind of got ahead of myself, right? I could have said for one, comma, blah, 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 to tell the reader I'm doing part one. But I went ahead and went for it, and now I'm just telling the reader I'm done with number one. Okay, so now we need to do two. Okay, so that's not too bad. Okay, so I'm going to come up here, and we'll do two. Okay, so I'm continuing with the proof. I'm going to leave this here so we can see it. Let's work backwards for a second. Okay, so again, I'm trying to get to AC is congruent to BD mod N. So that means N divides AC minus BD, which means AC minus BD is N times some integer, okay? So this is what we need to get to. Once we get to here, that will be true and that will be true, and we will have our proof. Now you might think to yourself, well, in the previous example, we had A's, B's, C's, and D's, and we added these two expressions, A minus B and C minus D, to get what we want. It's reasonable to think, what if I had A minus B here, and I had C minus D, and we multiplied them? We added them before, because this was addition. What if we multiply? Well, if you FOIL this out, you're going to get AC minus BC minus AD plus BD. So you get all this extra stuff. We do want AC, we want AC minus BD. We don't have the minus there, and we get extra stuff we don't need. Now that was reasonable to try. It worked for addition. It makes sense to try it for multiplication. Unfortunately, it doesn't work, okay? So we have to try something else. Okay, now I have an AC and a BD. There's 4 variables involved here. If we can maybe get it down to 2 variables, we might have a pair. That's my thinking. If you look in the book, the proof the book does here is not what I'm doing here, because yeah, I mean, it's an easy proof if you can figure it out. So if you read the proof in the book, it'll make sense to you, and you'll follow it just fine. But again, my thinking is that I'm going to start with AC minus BD. I have 4 variables. If I could get rid of 2 of them, maybe it'll work out. Okay. So what I want to do is I want to solve for A here, and then I'll just have a B over here. Solve for C here. So then I get rid of A and C, and I'll have B's and D's and N's and K's. Okay, so that's what I'm going to do. So, so again, this has already been written. Part 1's been written. So for 2, let me write this. How do I want it? The previous work, from the work above, meaning this, we get, okay, so I'm going to solve for A here. So we get A is B plus NK1. So I'll solve for A. And solving for C, I get C is D plus NK2. Again, if the reader just looks above, they'll see what I did, I hope. And again, because it's been a while since that's why I said from the work above, the reader knows to look further back. Okay, so thus, now I'm interested in doing this. So let me do AC minus BD, AC minus BD. Well, I just said A is this quantity and C is this quantity, so let's substitute. B plus NK1, D plus NK2, and then minus BD. Okay. Now, if you might be inclined, the way I'm doing this, again, the book is doing a different proof, you might be inclined, well, let's solve for B here. I solve for A and C. What if we solve for B and solve for D and put those in here? Well, what happens is everything drops out and you get AC minus BD. So you get AC minus BD is AC minus BD, and that doesn't get you anywhere. Again, my thinking was I had 4 variables here. Notice A and C are now gone. That's my thinking. So if I continue here, equals, if I follow this out, I get BD plus BK2N plus DK1N plus N squared K1 K2 minus BD. So BD, BK2N, DK1N, and then N squared K1 K2. I'll put the 2 in the wrong place. K1 K2 minus BD. And notice what happens, the BDs drop out, and every other term has an N in it. So if you want to add another step for the reader, you can just subtract the BDs out. And then factor out a single N. So I get BK2 plus DK1 plus NK1 K2. Good. I ran out of room. N BK2, DK1, and then NK1 K2. So notice what I have. I have AC minus BD is N times an integer. Every single one of these, A, B, C, D are integers. BD, K1, K2, N are integers. Hence, what do we have? N divides AC minus BD, and therefore AC is congruent to BD mod N. And then, just to say we're done with everything, this completes the proof. That tells the reader we've done both parts. And a little black square at the end to say that we're done. Okay, so there's my proof for this result. So what does this say? Like I mentioned before, when we're just doing real numbers, right? If you have 2 real numbers that are equal and 2 real numbers are equal, if you add the A plus C and B plus D, that's true. If you multiply A, C, and B, it's true. That result extends when you are doing modular arithmetic here. So if A is congruent to B mod N and C is congruent to D mod N, if you add these and add these, those will be congruent mod N. Same with multiplication. Okay, and we need this result later. That's why we're spending a lot of time doing this. Okay, so let's move on. The next definition says, and we played around with this idea last time, even though we didn't use this definition. So we want to look at, pick your favorite integer at A, and pick an n to use mod n. And again, the definition says n has to be positive, but usually n's at least 2. So we usually don't do n as 1. Okay, so A and n are integers and n is positive. The congruence class of A modulo n, okay, we represent that by bracket A. So this is the congruence class of A modulo n. Okay, so the definition says, for those that haven't had me before, that's a brace. Braces are supposed to look pretty like this, but mine usually just wind up being a squiggle, just so you know. Okay, so it's all the integers that are congruent to A mod n. Okay, so the class of A, it's every integer that's congruent to A mod n. So it's all the B's that are congruent to A mod n. And they said, there's a notation. If you're working in more than one modulus, You might say the congruence class of A mod 3 or the congruence class of A mod 7. So if you're working with two different mods, they'll put a subscript here. But we're typically going to only work with one mod at a time, so you'll just know from context which one it is. Okay? Okay, so the thing is, this is cumbersome. And we did this the other day. Let's get a user-friendly version of this definition. Okay, so suppose we're trying to find the congruence class mod A. Let's pick a B in that class. So what does that mean? B is an integer, and B is congruent to A mod N, whatever N is. Okay, so what does that mean? The definition of mod means N divides, I'm just going to write A, no, I'll write B minus A. Right? N divides B minus A. If you write A minus B, it's the same thing. So B minus A is N times some integer, I'll just put K. So what is B? B turns out to be A plus NK. We did the same calculation the other day. Okay? So if B is in the congruence class with A, B must look like this. A plus a multiple K of N. So we can actually rewrite this set. So the congruent class of A is the same thing as the set of all A plus Kn, where K is some arbitrary integer. Right? Okay? So you don't have to worry. I mean, understand that that's what this means, right? The congruent class of A are all the integers that are congruent to A mod N. But what does those turn out to be? It's whatever congruence class A, it's A plus multiples of N. Okay? So this is a much user-friendly definition than this, because you don't have to figure out everything that's congruent to A. There's a description that tells you what's congruent to A. So that's the description we want to use. Okay? And it's easy to use. So as an example on the next page, it says in congruence mod 7, so that's N is 7, find that, so we're in mod 7, let me write that, mod 7. So N is 7. It says find the congruence class of 6, okay? So you want everything, all the integers that are congruent to 6 mod 7. Well, let's use our definition. That's the definition. This is our characterization, what we found out. So the congruence class of 6 is 6 plus K is some arbitrary integer, and N is 7. Right? So I just put A is 6, and I put N is 7. Okay? So what if we listed some, now this is an infinite set. Okay, let me leave some space here. Suppose K is 0. If K is 0, we get 6. And if K is 1, we get 13. And if K is 2, we get 20, right? Now what if we go with negatives, right? If K is negative 1, I'll get a negative 1, don't I? And if K is negative 2, I get negative 8, don't I? So I have dots on either end to indicate the pattern continues in both directions. Now keep in mind, right, we're doing mod 7, so it's multiples of 7, and notice the difference between each of these is 7. So once you have the 6, the starting point, add 7, add 7, add 7, add 7, subtract 7, subtract 7, subtract 7. So that's what, you really don't have to write this out either, right? Start with the 6, the congruence class you're trying to find, add 7, subtract 7. So whatever the end, it's not always 7, it's whatever you're modding by. So add 7, subtract 7. Now, they want also in this example to find the congruence class of negative 8 as well. Well, I could do the same thing, but from what I just said, right, when K is 0, you're going to get negative 8. And now we want to add 7. So if I add 7, I get minus 1. Add 7, I get 6. And if I subtract 7, I get minus 15. If I subtract 7, I get negative 22. Now, what do you notice about these two classes? So, again, both of these are in mod 7. If you wanted to, you could put the 7 here. It's not necessary in this problem. All right? So the congruence class of 6 and the congruence class of negative 8, you notice they're the same thing. Right? If I kept adding 7s here, I'm going to get these numbers. If I keep subtracting 7s, I'm going to get these. In this example, the congruence class of 6 is the congruence class of negative 8. It's the same class. Okay? Now, what was the point of this? I want you to realize that one congruence class, the representation could be two different things. So the congruence class of 6 is this, the congruence class of negative 8 is this, but they're the same set. So these two are actually the same. Now, it should not surprise you. Any number in either one of these you could use as a representative to write it down. This is also the congruence class of -1. If I did the same thing for -1, you're going to get the same set. It's also the congruence class of -22. So any number in the sets you could use as the representative here. Okay, so keep in mind, you may write it as congruence class of 6. Your friend may write congruence class of -8. You're both correct in this example. They're the same. Or look, if you look in the back of the book, they may call it something this. You may call it this. You need to realize they're the same thing. But what do? Just keep subtracting 7s from 6. You'll get -22, and then you'll realize they're the same class. Okay? Okay, so the next result here, this theorem 2.3, is dealing with congruence classes here. Okay, so the theorem says A is congruent to C mod N if and only if the class with A is the class with C. So that we sort of saw that in our previous example, okay? So how can you figure out if two classes are the same? Well, if the two representatives, if A and C are the representatives here I'm using to write the congruence classes, if A is congruent to C mod N, the classes are the same. Okay, so let's do the proof here. Now remember, if and only if means if A is congruent to C mod N, then the congruence class of A is congruent to class of C. And then you have to go the other way. If the congruence classes are equal, then A is congruent to C mod N. It's if and only if. You have to go both directions. So I'm just going to do this the forward direction. So let's assume A is congruent to C mod N. Okay. So I'm assuming the hypothesis here. Now, I don't have to go to equations and everything like I did before, because we have some machinery now with congruence classes, right? In discrete math, we went congruence class to divisibility to equations, and then back to divisibility and congruence classes, because we didn't have any results on congruence classes or divisibility for that matter. Okay, but now we have some machinery. I don't have to do that. Right? Now, the problem here is, notice I'm assuming the hypothesis. I need to show the congruence classes are equal. These are sets. To show two sets are equal, you have to show containment both ways. So to show the congruent class of A is a congruence class of C, you have to show the congruence class of A is a subset of the class with C, and the class with C is a subset of the class with A, right? That's what you have to show. Now, we're only going to do one of them, and then we're just going to say the other way works exactly the same. But if they didn't work the same, you'd have to actually work them both out to reach this conclusion. So this is saying the same thing as that. Okay, so now how do you show? Yeah, I want to show these two sets are equal. So how do you show something? One thing is a subset of another. You pick an element in here, and you show that element you choose is in there. So again, this is all stuff you learned in Math 223, and you have to remember all this. To show this set is a subset of that set, that's what I want to do. I'm going to pick an element in this first set. So let B, I'm just picking B, to be an element of the congruence class with A. So I'm choosing a B in here. I need to show that B is in here, and then I'll have subset. Now, what does it mean for B to be in the congruence class of A? Our definition said, right, if you're in the congruence class with A, that means B is congruent to A mod N. That was the definition, right? The congruence class of A is everything in the integers that's congruent to A. So if B is in this class, B and A are congruent. Okay. Now, notice we already said A is congruent to C mod N. So we already assumed that. So I have A is congruent to C, and B is congruent to A mod N. So since A is congruent to C mod N, we conclude that B is congruent to C mod N by theorem 2.1. Now that's the reflexive symmetric transitivity. Okay, so yeah, we're really just using transitivity here, right? We have B is congruent to A, and A is congruent to C, so B is congruent to C. That's transitivity, right? Transitivity is if one thing is related to a second, and the second is related to the third, the first is related to the third. So B, the first, is related to the second A. The second A is related to the third C, so B is related to the third by transitivity, which is what we did by theorem 2.1. Okay, but if B is congruent to C mod n, what does that mean? That means B is in the congruence class of C, because the congruence class of C is everything congruent to C. If B is in that class, B is congruent to C. Well, vice versa. Since B is congruent to C, B is in the class with C. So what do we have here? Let me put a comma. Right? So I started with B in the class with A. I just got B was in the class of C. So that means the class with A is a subset of the class with C. Right? I started with an element B in here. I showed the element B was in here. That means this set's a subset of that set, and that's where we are. So the class with A is a subset of the class, congruence class with C. Okay, now again, I'm not going to go the other way because it's similar. I would start with B in here and get B in here, and it's the exact same proof with A and C switched. So a similar argument yields the class with C is a subset of the class with A, and we get the class with A is the class with C. Now, notice I'm using equals here. It's not the triple, right? This is a set of numbers. This is a set of numbers, and we know what it means for two sets to be equal. We don't say two sets are congruent here, right? Elements, right? Integers are congruent to one another, not the sets. Okay, so we did this direction, right? We assumed that, we showed that. Now we need to go the other way. Okay, so for the other direction, I'm going to say, oops, now assume, you could say for the converse, tell the reader going the other way. So I'm going to say now assume the class with A is the class with C. So the reader knows I'm going the other direction now. Okay. So since A is congruent to itself, mod n, by theorem 2.1, that was the reflexive property, right? We showed A is always congruent to itself in any mod. Right? We see that A is in the class with A. Remember when I did those examples a little while ago? I always said start with that representative. That's when the K was 0. A is always in its own equivalence congruence class. Okay? But we just explained it. A is congruent to itself, so A is in its own congruence class. But we just said the class with A is a class with C. So A is also in the congruence class of C, because we just said A and C, this class with A and C are equal. And so what does that mean? What does it mean for A to be in the congruence class of C? That means A and C are congruent mod n, which is what we were trying to show. Okay, so there's the other direction. Right, so there's a lot of, using things for it. Notice I never went to divisibility, and I never went to equations like we did before, because our theorem on we didn't use the previous one. The theorem on reflexive symmetric transit, that's what theorem 2.1, that's what we used here. So as you build up machinery, you don't have to go back to divisibility and equations anymore. Okay, so let's continue with a corollary. So corollary 2.4. Now remember, corollary is a small result that usually comes immediately or without too much work from a theorem. And it's like, well, if you already have a big theorem, why do you want a corollary? Because usually there may be a special case you're interested in. And so you just want to say, here's the result for the special case we're going to use a lot. So you don't have to use the theorem. So corollary 2.4 says, two congruence classes mod n, so the same n, are either disjoint, meaning they have nothing in common, the intersection is the empty set, or identical, meaning they're the same thing. So if you take one congruence class, congruence class with A, and you take another congruence class or congruence class with C, and you have something in common, this picture's not going to happen. Okay? So either, what does this say? You're going to have a congruence class here and a congruence class here, and they have nothing in common, or you have congruence class with A. If it has anything in common with it, it actually is equal to it. So they either completely disjoint or they're the same thing. So that's a nice result, because you're not going to have, there's some things in A that aren't in C, there's some things in C that aren't in A. This can't happen. Okay, so two congruence classes for the same mod n are either going to have nothing in common or everything in common. So that's what we want to prove. Okay, so here's the proof of corollary 2.4. Two congruence classes modulo n are either disjoint or identical. Okay, so let's just assume our classes are A and C. That's what we've been doing. So if the congruence class with A intersect the congruence class with C is empty, then we are done. I know that sounds fun to say that math, but that's a standard phrase. We are done, meaning there's nothing to prove, right? If we pick two congruence classes and the intersection is the empty set, we satisfy the corollary. Two congruence classes might are either disjoint or identical. So if we choose two classes and they're disjoint, we're done. They're disjoint and we're good. Okay? So let's assume they're not. So assume the two classes with A and C is not the empty set. So there's something in both of those. And let me just say that. Thus, there exists a B in that intersection. Okay? Okay, so that's where we are. So if the intersection of the two congruence classes is empty, there's nothing to show, they're disjoint. So let's assume the intersection's not empty. So now we need to show that the class with A and the class with C are the same class. So that would get identical. Okay? Okay, so B is in the class with A and the class with C. So since B is in the class with A, B is congruent to A mod N. That's the definition. If B is in the congruence class of A, B is congruent to A. That was our definition. Likewise, since B is in the class with C, we said that here, B is congruent to C mod N. Okay, same reasoning. So by symmetry and transitivity, I'm using that theorem 2.1, I just didn't write it. So transitivity, we get A is congruent to C mod N. Okay, now let's see why, I wrote it down, let's see why that is. Okay. Before we just used transitivity, now I'm saying symmetry too. Because you could say the first to the second and the first to the third. See, you need to rewrite one of these. Like if I switch these, right, symmetry. B is congruent to A, so A is congruent to B. So then I have A to B and B to C, so A to C. That's where that's coming from. So the symmetry, they're just saying switch these. So you don't want first to second and first to third. You want 1 to 2 and 2 to 3. So if you switch these, you'll have A to B. So A is 1 to B is 2, 2 to 3. So A is congruent to C mod N. So that's that theorem, 2.1 again. Right? So hence, what does it mean? If A is congruent to C mod N, that means those two classes are equal by the theorem we just proved, by theorem 2.3. Right? We proved that if two integers are congruent mod N, their two classes are the same. So, I mean, this wasn't that hard, but we really needed the machinery from theorem 2.3 to go from here to here. Okay? So let's write the conclusion. Therefore, two congruence classes, I'm just restating the theorem, two congruence classes modulo N are either disjoint or identical. That's what we showed. And there's the end of our proof. So that's a nice result, telling us a lot about congruence classes. So if you pick two congruence classes, mod N, the same N, they're either going to have nothing in common or everything in common. They're either disjoint or they're identical to one another. Okay, so we have a corollary here. We're not going to prove. If you think about it, it sort of makes sense. But so it's more about these classes. And this is dealing with the thing I had before, with the class with, what it was, the class with 6 and the class with -8 were the exact same class. And so you have to realize the class with 6 is a class with -8. But that was easy because 6 and -8 are congruent mod 7. So you know they're the same class. Okay. So it says, let n be bigger than 1, consider congruence mod n. If A is any integer and R is the remainder when A is divided by n, then the class with A is a class with R. Okay, so A is some integer, R is the remainder when you divide A by n. Remember when we're doing division algorithm? Now you have to be careful, right? if A were negative, you can't say, remember, the negative divided by n, and you remember we had to round up to figure out what R was. Okay, so this is going back to division algorithm. So they're saying if R is the remainder when you dividing A by n, so they don't actually mean dividing, they mean using division algorithm, then the class with A is the class with R. Okay, now if you think about it, remember when we did division algorithm, right? If you divide A by n, A is going to be some kn plus some remainder, but what was the restriction on the remainder R? R was between 0 and n. R could be 0, but we didn't let R be n because then you cycle back around to the remainder is 0 case. So in this situation, right, every class, mod n, can be described by just looking at the remainders. But how many remainders are there? R could be 0, 1, 2, all the way up to n minus 1. Okay? So since there are these many choices for R, there's n choices for R, right? And every class can be described by a remainder. That means there's n classes. So we haven't seen that. That's our first result on how many classes you're going to have. So if you're doing modulo 7, there's going to be 7 classes. I mean, we talked about this before with division algorithm, right? We said there was R choices for the remainder, but because of this result here, right, all the classes can be described by the remainders. And since they're n remainders by the division algorithm, there's n classes. Okay, so the example here says find all congruence classes modulo 4. So n is 4. List the elements in each class. Okay, so I want congruence classes modulo 4. So n is 4. Now if we're doing congruence classes mod 4, what are the possible remainders? 0, 1, 2, 3. There's your 4 classes. Okay, that's what this sim tells me. If you're doing mod 4, there's 4 classes, and just put the possible remainders by the division algorithm. Okay, so we want the class with 0, we want the class with 1, we want the class with 2, we want the class with 3. Now remember, any 2 congruence classes are either identical or they don't have anything in common. So if you list elements here, it said to list elements. If you get something in common, only 1 or 2 things in common, you've made a mistake, because you're going to get the same list again or they're going to have nothing in common. Okay, so I'm going to do what I did before and just start with the 0. And now how do you get other elements? You add the 4 to it, right? So that's 0, 4, 8, dot, 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 and subtract 4, you get minus 4, minus 8, dot, dot, dot. So there's the class with 0. Now what's the class with 1? Start with 1 and add 4. So I get 5, 9, dot, dot, dot. Subtract 4, you get negative 3. Subtract 4, you get negative 7, dot, dot, dot. Notice I don't have anything in common. They shouldn't have, right? I mean, these are the different classes. Okay, that's what I'm saying. If you just choose the remainders for the representatives, they won't. They will all be different. So if we do 2, we're adding 4, so that's 6, 10, dot, dot, dot. Subtract 4, you get negative 2, negative 6, dot, dot, dot. And then lastly, let's do 3, 3, 7, add 4, dot, dot, dot. Again, I'm just doing a couple each way. And subtract 4, subtract 4. Notice I have negative 8, negative 7, negative 6, negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice every integer is in one of the equivalence classes. That's what we learned by the division algorithm. Remember, every integer can be written one certain way. And so every integer is going to show up somewhere. And notice any 2 classes I picked are disjoint, right? They don't have anything in common. So there's the 4 classes. Mod 4. Okay. Now the notation we use to denote the set of all congruence classes for a fixed n is z sub n. So z stands for the integers, the big Z, and you put in. So big Z mod n. Okay. This means the set of congruence classes mod n. Okay. So the example says, let's list all the classes for Z4. Okay. We just did. So it's the class with 0, the class with 1 that we just did, the class with 2, and the class with 3. There's Z4. It's that right there. I'm not going to list all the elements, but we just did that. Okay, so Z4 are these 4 sets. So Z4 is a set of sets. Okay, it says do the same for Z2. So Z2, well, whoops. Well, think about Z2. If we were going to do all this again, well, how many classes would we have? Well, when you're in Zn, right? Zn has n congruence classes. Z4 had 4 congruence classes. Z2 is going to have 2 congruence classes. Now, what do we choose for the classes? Well, you use what are the possible values for R for the remainder when n is 1. So you're going to have the class when n is 2. The class was 0 and the class with 1. That's it. Okay. Remember the previous theorem said there are n classes running from 0 to n minus 1. Right? So 4, we went from 0 to 3. For 2, you went from 0 to 1. Okay, so Z2 has 2 classes, Z4 has 4. They go from 0 to n minus 1. Okay, now obviously you could use other representatives if you wanted to. Right, like here it says list 4 classes in Z4. Okay, if I'd wanted to, I could have just said, remember the class with 0 is the same as the class, I could have said 0 is the class with 8. It's the same thing. I could have said the class with 1 is the class with -7. I could have said the class with 2 is the class with 10. I could have said the class with 3 is the class with -1. Right? This would be a correct answer, right? These are the same 4 classes, it's just the representatives are different. But in practice, we use the possible remainders so we're all on the same page. I mean, these would be the 4 different classes in Z4, but in practice, you want to use the positive integers here, okay? So typically, if you're in Zn, what are the classes? 0, 1, ... and the last one is n minus 1, okay? Now, you don't do n because notice 4 is in here. The class with 4 is the class with 0, okay? So 4 is in this class right here. So we use the 0, not the 4. So 0 to n minus 1. Okay, that got us through that section, and I think that's probably enough for this lecture.